nth roots of a complex number and how to compute the nth root of a given complex number z naught. But I think it's better for us to start with something more concrete and look at that example before we go on to the more general case of computing the nth root of any complex number z naught. And let's take the example of computing the cube's root of 1. Well, what does it mean to compute the cube's root of the number 1? Well, if we have a number which is the cubed root of 1, then what it means is, let's say, if we cube that number, we should get 1, right? That is what it means to take the cubed root of 1. So what we are, then we would say that then z is a cube root of 1. So what we are really asking for are, what are all the numbers z, which when you raise to power 3, you get 1. Now, at first it seems like a strange question, right? So clearly, if z is 1, then 1 cube is 1, but it seems like the only number that when you raise to power 3, you should get 1. Well, not quite, because if you restrict yourself to real numbers, then it's true that 1 is the only number which when you raise to power 3 will give you 1. But if you let z take complex numbers, then indeed you will see that there are more numbers which when you raise to power 3 give you 1. And in fact, it's going to turn out that you have exactly 3 numbers including 1, such that when you raise it to power 3 you get 1. And the reason you're going to have exactly 3 numbers is you can think of finding a cube root of z as asking for a solution to this equation. So any solution to the equation z cubed minus 1 is equal to 0 is a cube root of 1. Right? And if you think of this as an equation with z being the variable, then this is a third degree equation. And the fundamental theorem of algebra tells us that every nth degree equation has exactly n roots, if you allow for complex roots, and that means they should have 3 roots, and we're going to see how to find these 3 roots now. And the key idea we are going to use to find these 3 roots is to realize that the number 1 can be written in polar form as 1 times e to the j0. But we can also write e to the j0 as e to the j2 pi. And this is also the same as e to the j4 pi. And indeed, we can keep going like this, but you will see soon that it's not necessary to go any further. And I did make another video earlier where we talked about why e to the j theta is equal to e to the j theta is equal to e to the j times theta plus any integer multiple of 2 pi for any integer, k being an integer. Right? So I used k to be 1 and 2, and we know that this to be true. So now what we are really looking for is a number, a complex number z, such that if I raise z to the 3rd power, I should get either this, this, or this. Right? If I get any one of these 3, then we know that all of them are 1, so z cubed must be equal to 1. And you can see that if I set my z to be 1, which is e to the j0, then indeed z cubed is equal to 1. But that's not a very interesting answer, but we'll keep that. Now let's look at this expression for 1. And let's think about the complex number e to the j 2 pi over 3. And look at what happens if I cube this complex number. So I'm going to get e to the j 2 pi over 3 raised to power 3. which is nothing but e to the j 2 pi. And that is indeed equal to 1. So now I have found a number e to the j 2 pi over 3, which when I cube gives me 1. So e to the j 2 pi over 3 must be one of the cube roots of 1. Right? You can write this in Cartesian form. If you want to write this in Cartesian form, you will get negative 1/2 plus j times square root of 3 over 2. If you, if you want to confirm this, you can plug this into your calculator, cube it, and see that you get 1. Okay, so now we have found 2 cube roots. How about the third one? So you probably see the pattern here, right? So maybe I can find a number z, which when I cube will give me e to the j 4 pi, which is also the same as 1, right? Indeed, I could take e to the j 4 pi over 3. And that will give me, so if I cube that number, you can see what's going to happen. What's going to happen is this 3 and 3 are going to cancel out, and I'm going to get e to the j 4 pi. And e to the j 4 pi is indeed equal to 1. Oh, I need to be a little bit careful here. So what I meant was z is equal to negative 1/2 plus j times square root of 3 over 2. And in this case, you will see that z is negative 1/2 minus j times square root of 3 over 2. But these three numbers are cube roots of 1. Now, it's common to write them as 1. You write this as omega, and you notice that the third root is actually the square of the second root. So this is omega squared. And you can write them as 1 omega and omega squared. And these are the 3 cube roots of 1. It's quite nice to look at a geometric picture showing where the 3 cube roots of 1 lie. So you can see that one of the cube roots is just the number 1. So that lies along the real axis on the unit circle, because it lies at a distance of 1 from the origin. Another cube root, which is e to the j 2 pi over 3. Notice that the magnitude is 1, so this also lies on the unit circle. And it makes an angle of 2 pi over 3, which is 120 degrees with respect to the positive real axis. Now the third root is e to the j 4 pi over 3, so this makes an angle of 240 degrees or negative 120 degrees. And you can see that these three things should be cube roots if you interpret the action of cubing them as multiplying the complex number with itself. So remember, in an earlier video, I showed that when you multiply a complex number with another complex number, you are scaling the magnitude by the magnitude of the second complex number and rotating the complex number by its angle. So if you take omega and you cube omega, so what you are doing is, and since the magnitude is 1, the magnitude is not going to change when you multiply omega by itself. So if you start with omega and you multiply omega with itself, you are going to rotate this vector by 120 degrees, and that's going to lie over here. So this is omega squared. Now when I multiply omega squared one more time by omega, I'm going to rotate it further by 120 degrees, and notice that I'm going to land exactly on 1, telling us that omega cube is indeed equal to 1. And you can check that's going to be true when I multiply omega cube by itself 2 more times. Because if I start with omega cube and I multiply it with itself, I would rotate this vector by 240 degrees, and I will end up here. So that would be omega square square. And then when I multiply it another time, I would rotate by another 240 degrees, and I would land exactly on 1, saying that if I were to cube this number, I would also get 1. So indeed, these are the 3 cube roots of 1. So at this point, I would like you to think about what you think will happen if you take, let's say, the fifth root of 1 or fourth root of 1, or think about what would happen to some other root of 1, and how you may be able to generalize this to taking nth roots of arbitrary complex numbers. I would urge you to think about it before you watch the next video, where I will talk about how to compute this for any complex number. And also keep in mind that if you just take the square root of 1, you would have gotten 1 as one answer and negative 1 as the other answer. But if you think about negative 1 as a complex number with an angle of 180 degrees, indeed, when you multiply negative 1 by itself, you would rotate that by another 180 degrees and you would land exactly at 1. So just telling us that both 1 and negative 1 are square roots of 1. But having said that, normally when we talk about square roots, we assume that you take only the positive value of the square root as the answer. Even though there are two numbers which when you square give you 1, you say that only 1 is the square root of 1, and that's by convention, and we call that as the principal value of the square root. In the same way, we can by convention use one of these three roots as the principal square root, and typically you just take this one, which you get by not adding any multiple of 2 pi to 0, you take that as the principal value. But all these three numbers, if you cube them, will give you 1.